Hello students, for video 15c we're going to talk about some different kinds of components that are used in welding fixtures in industry. So we're going to talk specifically about the clamping components and some of the pistons that Mr. Otten uses regularly. So here is a part that we're going to consider for the next fixture example. So some things that we see on this part when we look at it. On the welding callout, we see that the leg length of the weld is an 1/8 inch. So that's a really small leg length of the weld. We see that it's a fillet weld, and we see that we want the outside edge to be convex. We see that there are going to be 4 of them. And all of this is happening on the side that the arrow is pointing to. And so that's going to be these sides right here. So we're going to be, well, that's unfortunate. We're going to be doing it on this side right here and that side right there, and then the other sides on the outside. So we have to be able to get to the outside of this. Some things that we also learn about it is that there is no welding that's happening along this little line. So why would that be? Well, this probably slides in. It is a grease reservoir, so it probably needs to slide in pretty close underneath another place that it's catching the grease, from which it's catching the grease. And so a little bump right here might cause it to not slide into place very well. Also, with the grease reservoir, it's something that the employees are going to deal with, but it's not something that the that anybody else is going to see very often. So it's not really important, quite as important how it looks. But when we look at the notes down here, one is that everything needs to be deburred and the sharp edges need to be broken, and welds must be solid, and the welds are going to be sandblasted. So what that tells us is this is something that's going to get handled a lot, and these welds need to be nice and smooth. The edges and corners need to be nice and smooth so that nobody gets cut while they're sliding this into and out of the pizza oven. You can see that it's pretty big. In the unfolded state, it's 25 inches long and 14.5 inches wide. So it's probably, 18, 20 inches long when folded, and maybe 10 inches wide or so. Okay, so let's look, let's see, one other thing is, notice that there's a flange on the end, a flange on the left side, and a flange on the other end, but the back does not have a flange on it. So we have to think about that when we clamp this thing up. We have to be able to get to the outside edges, but we also have to be careful of these flanges, because once it is all welded together, however we're clamping it has to move far enough out of the way that it won't get caught on these flanges. So let's look at it and see how it's done. This gray part right here is the part that we just saw, the grease reservoir. It's upside down. Notice that the side that had no flanges to the right, and you can see the flanges right here and right here. This is that little edge that we're not supposed to weld, but this is the edge that we're supposed to weld. So 1, 2, and then the back 2 over there. Okay, so some interesting things about this. One of them was that it's really hard to tell how this is being held in place unless you know something about the way that Mr. Otten does his simplification. And so one thing that he does is he has this bar, and it's got a mounting block on it, and then he's got just a drawing floating in space, and that drawing consists of this plate and then 2 screws up here. And what he's actually showing you is a clamp, a type of toggle clamp that he uses a lot, that's called a Destaco clamp. And all he's showing is this is how it's going to contact the part. This brown bar is going to contact the part and push it into place. But he's not drawing out all of the clamp components, and that's partially just to simplify the model so that there's less to look at, but also less for Mastercam to have to deal with. So you can see there's actually a clamp here and one here, and then on the two sides, and on the I guess there is not one on the back. He just has a solid bar holding it on the back, and then two solid bars on the right side that are holding it, because you can use those as locators and just clamp from the opposite side. So let me show you one of these Destaco clamps. If I hit the right button here, which that was not it. That's a better button to hit. Okay, so this is a Destaco clamp, and you can see that as I clamp it, this bar, this is representative of the brown bar that you saw in the other piece, that bar swings into place and pushes in sideways and also applies a downward force. And so what he has modeled is this plate down here where it mounts, and then these two screws that go through this top of the clamp to the bar that you make. So you buy this part right here, and then you make these attachment points as a custom-made item. Now, we'll see that there are several types of Destaco clamps. So Destaco is DE-STA-CO. They make a ton of different kinds of clamping solutions. They're a really good company for that. Now this one, when it is in the clamp position, the arm is vertically up, and that could get in the way of our welding robot. So the clamp that he actually uses, that we'll see in a minute, when it's in the clamp position, the arm is actually horizontal and it's back out of the way. And that's just different kinds of clamps that you can get. Now these clamps have a lot of different connections and joints in them. And so I don't know if you can hear that or not, but there's a little bit of compliance in there. I can kind of wiggle this clamp around. So this clamp would generally not be a good enough clamp for machining unless it were pretty low accuracy machining with fairly low loads. But it's a great kind of clamp to use for something like welding, which doesn't have very high forces in the welding process. Now it's a little weird that he puts this bar up on top of the clamp. Most people use these with the bar underneath the clamp, but he's actually done analysis of the motion of the clamp, and if you put things underneath, then they actually draw back in just a little bit. And if you put them on top, just because of the relative angles of all these places, when it comes into position, it is pushing down and still pushing inward some. And so he can get the right kind of motion that he needs that way. Notice that he's done some extra work on this. He's put this nice radiused edge here on the part so that as it comes in and hits the part that he's trying to make, it's not going to scratch it up. There are other kinds of these Destaco clamps. You can do all sorts of things with them. Here is one that just applies axial pressure, so you can see it does not do any of the downward force, it just applies force inwards. And so if you need that, you can use one of these. They have a threaded end on them, so you would make the thing that contacts your part and thread it into the end. And so just another clamping solution from Destaco. All right, let's go back and look at the drawing a little bit more and see some other things. Okay, now there's also something going on inside this part. So there's one of these right here. There would be another grease reservoir over on the right side. And some of the things we notice is that he has something that's inside that is pushing outward into the corner. So he's going to clamp on the outside of this with those Destaco toggle clamps, but then there's this blue thing that is pushing over to the side, and it's a little tricky to tell what this is, but you can see that he's got another drawing in there, and it's a drawing of 4 mounting points there and 2 mounting points on the back. And then you can see there's a little drawing of the end of a cylinder. Well, what is he doing with this? It turns out what he's doing is he is putting a heat sink and a clamp on the inside of each corner. So on this part, because it's a grease reservoir, it's really important that the weld be good all the way top to bottom so that it doesn't leak any grease out. And for whatever reason, in the process, he felt that this weld needed to have heat pulled out of it while the weld was occurring, and also it needed to be pushed from the inside as well as the outside to make sure that the pieces were where he wanted them to be. So there we go. Here is one of the heat sinks he uses. You can see that this is a brass heat sink. It's shaped like that one that's in the drawing, and he uses brass heat sinks sometimes. They're much more expensive, so when he can, he'll use an aluminum heat sink. But this just gets pushed into the corner on the inside of a part, and when it's pushed into the corner, then it's going to pull the heat out into the heat sink. One thing you'll notice about this is there's not a very big conduction path, and the conduction of heat goes as K, that's a heat conduction coefficient, the thermal conductivity, times A, which is the cross-sectional area of the flow path, times the delta T, so the difference in temperature between the low and the high temperature. So this A, this cross-sectional area is really small. So not very much heat is going to flow out of this. You actually have to do it that way because you don't want to put very much heat back in here into this piston. And so all you can really do with this is you can absorb the heat into this block. And after this block heats up all the way, then it's not a very good heat sink anymore. But you can calculate that out and know what mass of material you have to have here and what material you have to have here. Brass has a much higher specific heat than aluminum, and so this can absorb a lot more heat before and it will rise a smaller amount of temperature for more heat absorbed. You can see that it's mounted on this piston. These pistons are made by a company called Bimba. That is kind of the standard piston company for this side. This is called a flat one sometimes. Yeah, and so the one is a 1 inch, so that's nominally a 1 inch diameter. You can get them in all kinds of different diameters and all sorts of different lengths. A bigger diameter means that it has more pushing force. A longer length means that it has more stroke. So you can see this is a 1 inch long, 1 inch diameter piston. It has about 3/4 inch length of stroke. A little bit of, yeah, around a 3/4 inch length of stroke. And that's because at each end there has to be a little space. This is a double acting piston, so you can put air on one of these fittings and it will extend. You can put air on the other fitting and it will return. And so that allows you to extend that into the corner but then return it so it's out of the way to be able to get the part out. Here are some of those speed controls that I talked about before, where it has a little needle valve on top. It also has a locking screw, so once you find the correct setting for your needle valve, you can lock this, this nut down, and that will keep it from adjusting on you when you don't want it to. Again, these just slow down the rate that the air is moving. Wanted to show you one other style of heat sink that he uses. So this is a heat sink that he made that just goes against a large surface, just trying to draw out as much heat as it can, also do some work in clamping things in place. And so this one's made out of aluminum, so that means it will cost about 1/4 of the brass one, and it also cannot absorb as much energy before it heats up. Okay, so looking back at the drawing for a minute, that's really a lot of what is in this fixture. So let's look at the real fixture. Here it is. You can see the grease reservoir. You can see the toggle clamps. Like I said, he uses toggle clamps with the horizontal face on them. We can't really see in very well. I guess you can right there. There is one of the pistons that is pushing into the corner of the other reservoir. You'll notice that it's an aluminum piston in this case, or an aluminum heatsink, and so there must not be so much heat that has to be absorbed. Also notice that down here where there are plastic lines that might be subject to heat and radiation has covers over them. And so there is the thing all opened up. You can see there are 4 pistons on the inside corners. The fixed edges, turned out there were clamps in the back. It was hard to tell that on the drawing, but there are clamps on 3 sides, and then this is just rigid on 2 sides. Okay, how do you get away with clamps on 3 sides? Well, it's non-deterministic, and we have these pistons pushing against everything, so it will equalize the whole system. Okay, in the next video, we're going to talk about a last set of components that he really likes to use, and talk about some of the ways that he connects things together in his fixtures. See you there.